All right, Chemistry 3101. I just wanted to go over the table of IR absorption frequencies for specific functional groups. So you're going to be given this PDF for your next quiz, quiz 14. We're not going to worry about the values for NMR shifts right now, since we're just focusing on IR at the moment. So we're going to talk about this first table, IR absorption frequencies of specific functional groups. Again, this is chapter 14, and this is basically our version of the table. What is it, table 2 in your textbook? And so you will, again, be able to bring this in on your quiz. However, you will not have this table for your final exam. So an alkane is not a functional group. So if you're like, why did you put it in the table then? Well, it's just because alkane, sp3 hybridized carbon hydrogen stretching is so ubiquitous in organic chemistry that whenever you have something just below 3,000, you see that a lot of times in the infrared spectra that we look at. And so you'll know where it is. Now, if you have an alkene, for example, well, an alkene has a carbon-carbon double bond stretch, which is going to absorb around 1630, but you can also have the sp2 hybridized carbon-hydrogen stretching. Let's say we had an alkene like this, for example. Okay, we're going to have a dipole here, so that's going to give us this absorption. But then we also have the sp2 hybridized carbon-hydrogen bond, which is going to be just above 3,300. It's usually around 3,100 reciprocal centimeters. All right. Now, what about an alkyne? So if we have an alkyne, for example, if we have a triple bond like this, we're going to get an absorption around 2,100 to 2,150 reciprocal centimeters. If we have the sp hybridized carbon-hydrogen bond, that is going to absorb around 3,300. So something to look for there. Next is aromatic. So an aromatic ring. If you have an aromatic ring that looks like this, you're going to have a lot of, sp2 hybridized carbon-hydrogen stretches. So again, those come just above 3,000 in the 3,100 neighborhood. But when you have an aromatic ring, you have these alternating double and single bonds. Those will usually produce anywhere from 2 to 3 signals between, it says here 1,600. It's actually more like 1,450 to 1,600 reciprocal centimeters, actually. And you'll see, again, 2 to 3 stretches, 2 to 3 stretches for the carbon-carbon double bonds. The next one is an alcohol. An alcohol is one of the easier ones to recognize because you've got an oxygen-hydrogen bond. And I explained that those are going to give you a very broad absorption, around 36 to 3,200. You can also see stretching between the carbon and the oxygen, which is going to be in the neighborhood of 1,250 to 1,000. Next, we have an ether. So if we draw an ether looks like this. We only have the carbon-oxygen single bond stretches, which are in the neighborhood of 1,300 to 1,000. The next is the amine, and I spent some time explaining the difference between a primary and a secondary amine. But if we have an amine, looks something like this, right? Of course, you have nitrogen-hydrogen stretching, and I explained that in the last video. That's around 3,550 to 3,250 is where you look for those, and those are, again, usually quite a bit weaker, a lot weaker than the stretches that you see in an alcohol, even though they are broadened due to hydrogen bonding. Next is an aldehyde. What's an aldehyde? Well, in an aldehyde, we have a carbonyl, right? And then we have the carbon-hydrogen bond. Well, the carbonyl will give you a stretch around 1725. However, you also see what we call aldehydic carbon-hydrogen stretching at 2750 and 2850. So those are some numbers to remember because whenever you see an aldehyde, you will almost always see those. Next is a ketone. So 1750 is where we see the carbonyl stretch of a ketone. For an ester, it's at around 1735. So what's neat about an ester is a pretty unique group in infrared spectroscopy because not only do you see the carbonyl stretch at 1735, but the carbon-oxygen single bond stretch, this stretch here is oftentimes stronger than the carbonyl. So very strong absorbance in that 1,300 to 1,000 for an ester. very strong stretch. So those are usually a giveaway that you've got an ester. Next, the carboxylic acid is probably the easiest of all the functional groups to recognize in infrared spectroscopy. Why? Because the oxygen-hydrogen stretch is so broad. It covers like a third of the spectrum. It goes from 33 to 2400 reciprocal centimeters, and it can go beyond that a little bit. You've also got the carbonyl around 1700, and then you've also got the carbon-oxygen stretch, which is in between 1320 and 1210 is what it says here in our table. Let's keep going. After that, we have an amide. So an amide looks like this. It's like a carboxylic acid, but you have a nitrogen here. Okay, this is what we call a secondary amide. But if you have a nitrogen-hydrogen stretch, that's going to be in a broad range from 35 to 3000 or 3050-ish. Okay, but what's interesting about an amide is that the carbonyl stretch is weak. Okay, so it only absorbs around 1650, and that's because of the fact that there's a resonance structure that you can draw here, so it's weakened quite a bit. And then the last one is the nitrile. It's a functional group that doesn't come up a lot in this class, but it'll come up a little more in spectroscopy, the nitrile. So a nitrile is this, right? Don't confuse. This is cyanide, right? That's something that you would have learned in general chemistry, and you saw it as you'll also see it in organic chemistry 1, 2. But when you have a cyanide, basically attached to an organic compound, then it's called a nitrile, and the carbon-nitrogen triple bond will be around 25 or 2250 rather, in terms of its absorbance. Okay, so that covers all of the different absorbances in this table. Again, I will give you this table for your quiz.